So, good morning to all. Today we will discuss with one example different mapping scheme. As you can remember that we have started the mapping scheme like direct mapping, set associative mapping and the associative mapping. Okay. So, before having the discussion, we will start with a discussion over is something called the replacement policy, or it is something called the block replacement. As I said, the size of the cache memory is much smaller than the main memory. Okay. So, then what happened, and we introduce the mapping scheme. Since size is much smaller than the main memory, obviously at some point of time that cache memory will be full. So, that time you need to replace the some of the block by the incoming block. So, question is now which block should be replaced. So, that policy is called the replacement policies. Okay. Now, these replacement policies, one very famous replacement policies is oftenly used, that is something called LRU, that is place replacement policy is, there are many replacement policy and we will be knowing more in operating system class. In today's class, we will talk only one replacement policy, that is something called LRU, that is least recently used. Okay. So, LRU policy says that when the cache is full, that means all blocks are full, then you need to replace a particular, you need to first identify that which blocks should be replaced, and then incoming block will be placed in that particular block. So, in case of the least LRU, that is least recently used pages, the victim block is the block which has been used earliest point of time. Okay. It is not earliest point of time, sorry. So, the page that is the A block is the victim, a block is treated as the victim block which has not been referenced or referred, has not been referenced for longest period of time. Okay. So, that is it is called the least recently used pages. Okay. So, we should find a block. So, suppose you have cache memory, it has 1, 2, 4 blocks and all 4 blocks are full, then you need to find the block which has been referred long before. So, that is the victim page, and then we will replace that page with the incoming, sorry, not page, with incoming block. So, that is something called least recently used page replacement policy. So, how do you implement this one? Say suppose we have 4 blocks here, 1, 2, 3 blocks. With each block we should have a counter. Okay. So, there should be a counter here, there should be a counter, there should be a counter. Please note that we have already tagged with the each block. Now, we have to keep one counter with the each block. Okay. Now, there may be 3-4 scenario. Number 1, if hit occurs, number 1 is if, that means the block which the processor wants, it is within the cache memory. So, that is something called hit occurs. When we will say that hit occurs, if the processor wants a particular block, processor, as I said, processor will generate the address of the main memory. Okay. let us say main memory is 5 bytes, sorry 5 bit, and then processor generate the 5 bits. So, let us say 1 0 1 1 1, and let us say we use the direct mapping. Let us say this is the one block, 1 bit is used for the word, 2 is used for the what is called is block number, and this one is used for tag. So, this is tag, this is block, and this is word. Okay. So, now it will first check the block number. So, it will go to the third block. So, this is let us say this is block 0, this is block 1, this is block 2, this is block 3. So, obviously it will check here, it will go, and then it will check the tag. If this tag matches with the tag with 1 0, then obviously that page is the page that is referred by the processor. Then we will say hit occurs. Whenever the page is there in the cache memory, that wanted page is there in the cache memory. So, then that scenario is called the hit. So, when hit occurs, that means this, let us say processor wanted a page or processor wanted one address, let us say 1 0 1 0 1, then this is what? This is block, and this is tag, this is tag, this is block, this is what? Processor generate this address, that is 1 0 1 0 1, this is tag, this is B, this is what? Now, what processor generate this address, then memory module will match with this block. This block is nothing but the second block here 0 2, second block, and it will match the tag 1 0. So, it is matching with this tag 1 0. So, this tag is matched. Then memory module will be sure that this is the actually wanted block. If this is the block, means that block has been referred just now. Okay. So, now you see there is no space in this block. If there is all cache is full, then processor has to find a block which has been used for the longest period of time. Now, it has to keep somewhere that incoming pages. Now, if hit occurs, that means this is the desired page. So, no need to replacement for, because page is already there, but in some scenario it may happen that it needs replacement, then in that scenario you have to replace the one of the block. For that, what you will do it, now you have to keep the things ready. So, then whenever there is a miss, so you can replace the pages which are the oldest page, not only oldest page, it has been referred long before. So, therefore, what you have to do? So, the page which has been referred, this each is having, as I said, the counter, this page will have a counter 0 0, okay? And each block counter will change if the counter value is lesser than the old counter value of the referred page. That means, old counter value of the referred page was, let us say this is 1 0. Whenever a page will come, whenever a block will come to the cache memory, that block number, that counters will be set 0. Okay. So, initially all page this was 0, this was 0, all was 0 initially. So, what you have to do, whenever hit occur, then what you have to do, the for that particular block, that counter value we have to set 0, and for the all other counter which is lower than the old value of this counter will be incremented by 1. Let us say initially we have considered, let us say this counter is, let us say this counter value is 0 1, or let us say this counter value 0 1, this is 1 0, okay. This is 1 1, and this is 0 0. Now, the which page is referred, that is 1 0, that tag is, let us say this is the block B, okay. This is the block B, that is the this block, and then tag is match. So, what is the counter here? Counter is 1 1, okay, because this page is there here. So, counter is 1 1. What you have to do? You have to put 0 0 here, and the all values which is lower than this old value will be incremented by 1. So, this will be 1, this will be 3, and this will be 1 0. Now, if you see carefully that each page, each counter value is unique. So, this is no longer here 0 0 0 1 1 1 1 0. Now, you consider a scenario, let us say you have a tag 1 0, but block is let us say 0 1, it is possible. So, that is the 0 1 is this block. So, this is this side is I am saying ki block number, okay. This is block number and this is counter. Now, block number is 0 1. So, this is the block number and let us say tag is match also here, okay. Then what happened? So, you need to check the counter value. So, let us say old counter value was something like that. So, this is let us say 0 1, this is 1 1 and this is 0 0, this is old counter value. Now, the new page is referred. So, 0 1 block. So, this is the block, what is the value 0 1. So, this should be replaced by 0 0 because it has been referred just now, it is referred now, okay. And then whatever the value lower than the old values. So, lower than the old value 0 1 lower will be 0 0. So, this will be incremented by 0 1 and 0 0 will be incremented by 1 0, okay. And all other values will say this will remain here, right. So, it was 0 0, this will be it was 0 0. So, this will be 0 1, if it is 0 0 it will be 0 1 and it was 0 0. So, it cannot be 0 0 both. So, let me write it here once more. So, we have counter. So, let us say this counter is 0 0, this counter is 0 1, this counter is 1 0, this counter is 1 1. Now, it is referred 0 1. So, 0 1 means this block. So, this block has value 0 1. So, this will be replaced by 0 0 because it has been referred 0 0. Now, lower than 0 1 this is 0 0, right, lower than 0 1 is 0 0. So, this will be incremented by 1 0 1 and no need to do any other thing. Now, you see the value this is 0 0 0 1 1 0 1 1 all are unique. Now, what happened if the page is full, cache is full. Now, if you want to replace the page, if there is a miss, that page is not there, then what you have to do? You have to replace a page. Which page you should replace? The counter value 1 1 should be replaced because this is the page which has not been used for the longest period of time. So, therefore, this counter basically indicates that when that page was last referred or when the block was last referred. So, based on that we will take a decision that page will be replaced or not. So, this is the heat occur. So, this is the way you have to do. Now, if the miss occur and the set is not full. So, if miss occur, okay, and set or block is not full, one means there are spaces, block is not full. So, basically we are talking about the set associative memory case. So, miss occur, but block is not full, this is very simple. So, what we have to do? No need to replace anything, but you have to be ready with the system. So, that if there is a miss in future, then it will automatically or it immediately, not automatically, immediately it will replace the victim, it will replace the oldest page, okay, oldest referred page. Okay. So, therefore, what you have to do, or the page which referred long back, so that page you need to replace. So, therefore, when it miss occur, then what you have to do? So, what you have to do is, see, you bring the pages from the main memory to the cache memory and then counter will be 0 and all other counter value will be incremented by 1. Let us say you have 4 blocks. So, you have a counter here, you have a counter here, you have a counter here. Let us say here only 2 values are there, that means 2 blocks are occupied. So, obviously initially when it came it was 0 0. Now, when another block came, so that this value will be 0 0 and it will be incremented by 1. Now, miss occur, that means page is not there, but there are space in the cache. So, therefore, new incoming block will need to be placed here and then this should be 0 0 and this will be incremented by 1 0, this will be incremented by 0 1. Now, another block that is also miss. So, but there is a space in the cache memory. So, you bring another, let us say you bring another one here. So, then you set the value 0 0, this will be 0 1, this will be 1 1, this will be 1 0. Now, what will happen? Now, let us say scenario when miss occur, but set is full, that means there is no space. Then what you have to do? You have to replace one block. Which blocks you should replace? The counter value is the highest counter value, block with highest counter value should be replaced. So, highest counter value is this one, because this page was referred, as you see we mark first. So, it referred long before. Okay. So, then this content will be written back and the new block will come here. Now, this counter will change 0 0 and then value lower than this one. Okay. So, all values are lower, obviously you are going to target the oldest page. So, this is becoming 0 0 and then all counter value incremented by 1. So, this 0 0 will be 0 1, this will be 1 0, this will be 1 1. Okay. So, then we have three cases, one is hit occurs, then you change the particular block value, because that hit means that block is there in the cache memory. So, only the counter value will change, that will becoming 0 0 and the counter value for all other blocks will be incremented by 1 if the counter value is lesser than the old value of the referred counter, referred blocks counter. Okay. Now, if the miss occur, that means and then cache is not full. So, then you can place anywhere, but you have to increment the counter value by 1. And if the miss occur, then what you have to do? Set is full. So, you have to replace a block which has the highest counter value. Okay. You replace that block and all other counter value you incremented by 1. So, this is the page replacement policy. Okay. So, now what you do it? We have studied 3 mapping scheme, right. We have studied cache mapping scheme, we have studied replacement policy, especially that LRU. Okay. Now, we will see one example when we apply different mapping scheme and the replacement policy is the LRU. How the content of the cache will change, okay, based on the difference mapping scheme. Okay. So, I need to write the problem first and then we will go slowly. So, here problem is something here. By the way, I am teaching from amateur. A computer has separate data and instruction cache. Data cache has 8 blocks. Each block can hold one word. Each can hold one word. Okay. One word of 16 bit. So, no issue here. Okay. And number of set is 2. If you use the if set associative mapping is used. Okay. So, then computer has separate data and instruction. Data cache has 8 blocks, each block can hold one word, that means there are 8 blocks. So, number of set is 2 if set associative mapping is used. So, but what is missing? Missing is the what is the size of the main memory, right. So, otherwise we cannot proceed. So, consider that memory main memory consider main memory address is 16 bits, okay, and word is 16 bit. So, in each location instead of 1 byte there are 2 bytes of information in each location in the main memory as well as in the cache, okay, and it is total 16 bit in the main memory. Now, what you have to do is there are many things, you have a program, okay. So, while program is running you have to tell that what will be the cache content in different situation. So, let me first write the program here. Let us say if you have a program integer a 4 10, integer a 4 10, integer sum equal to 0, and then you have a loop j equal to 0, j less than 10, j plus plus, and what you have to do, basically you have to add the row content a 0 j, okay, and then you put a variable average equal to sum divided by 10. You have another loop for I equal to 9, I greater than equal to 0, I plus plus, what you have to do, a 0 I, basically normalization, a 0 I divided by average, and this array you consider the array A is organized in column order, and first element, that is a 0 0 is located at 7 a 0 0 location, okay. What you have to do, you have to say the show the cache content, so the cache content, if we use different mapping along with LRU replacement policy, okay. So, this is a problem. So, a computer has separate data and instruction cache. So, you assume that one instruction is there, only data is missing. So, data cache has 8 blocks, each block can hold 1 word. So, that means you have 8 blocks into the cache, and main memory is having 16 bit, and each block contain only 1 word. So, therefore, what will be the size of the word? So, if there are 2 words in a block, then you need to identify which block. So, you need only 1 bit, either 0 or 1, but here is only you have one word within a block. So, no need to invest any bits for identifying the word. So, then word will be 0, okay. And then another question is, it is in column order, and the first element is starting from the 7 is 0 0. So, therefore, what we can do it, we can write it here. So, first location is 7 a 0 0. So, if you write in hexadecimal, this will be 0 1 1 1, this will be 1 0 1 0, 0 0 0, okay, 0 0 0 0 0. So, this is a hexadecimal representation. So, this should be here, you have the array here, let us say total 40 elements, 40 into 10. So, this location you have a 0 0. Next location is a 0 1. So, this will remain same. So, it is in column order, that means this should be A 1 0. Okay. So, next is 7 A 0 2, this will be remain same, it will be 1 0 0 1 0, this will be A 2 0. Next this will be A 0 3, okay, 0 0 1 1. Okay. So, then this should be A 3 0. That means you have a array, it has 4 into row, right, 4 into 10. So, 1 2 3. So, you have 0 1 2 3 4 5 6. So, last one will be 9. So, this will be 0 1 2 3. So, it is column order, means this column. What is that? This column. This is 0 0. This will be what? This is 1 0. This will be 2 0. This will be 3 0. Next, this will be 0 1 1 1, then 2 1, then 3 1, right. So, therefore, next location will be A 0 4, this will be same 1 0 1 0 0 0 0, this will be 0 1 0 0. So, this will be A 0 1. Okay. So on. So, then total 40 elements. So, what will be the last element? 7 A 2 7, right. This will be 39. So, this will be what? 7 A is remain same, A will be 1 0 1 0, okay, and 2 7 0 0 1 0 0 1 1 1. So, this will be A what? 9 A 3 9. So, last element. Okay. Next what? Now, if we use the direct mapping, what will be the content of the cache? So, that is your question. So, before that, how do you divide the 16-bit main memory address into 3 field, that is word, block number and word, cache line, and then tag in case of the direct mapping. Let us say you have a address here or maybe here, then first word, how many words are there in a block? If it has more than one, then only you need to identify. If it is one, so block number is same as the word. So, therefore, there is no need for keeping separate, word will be 0. What next? Next is cache line. How many cache lines are there? 8 blocks. So, 8 means 3 bit. So, then 1 2 3, this 3 bit will identified as a cache line. So, this will give you the cache line, which cache it should be stored, and the rest will be tag in case of direct mapping. Now, in case of the associative mapping, what will be the situation? Associative mapping, if you remember, you had word, but word does not exist in this example, and then rest are tag. So, therefore, this all 16 bit will be the tag in case of associative mapping, right. Next is set associative mapping. Okay. In case of the set associative mapping, what is no doubt 0? Now, you have to identify which set. I think I say this is the, how many sets are there? There are 2 sets. So, therefore, you need 1 bit. So, therefore, in this example, this one, let us say I can write it here. So, this bit will identify the set number and rest will be the tag in case of set associative, tag and set, right. Now, cache content. So, first if you use the mapping, direct mapping, what is the page replacement policy? So, direct mapping there is no page replacement policy, because in particular block you have to place only. That is why we introduce the associative mapping. So, then what will be the content? Let us say what we do it, we identify block. Okay. So, let us say block 0, block 1, block 2, block 3, block 4, block 5, block 6, block 7. Okay. So, let us say we are drawing it like that, we will see the purpose. Okay. In case of direct mapping plus LRU. So, now you need to go to the program. Here we have the program. So, first what you need to access A00. So, A00 was there in the memory location 2700. Okay. So, you are using direct mapping. For direct mapping, so no word, only the cache line. So, then this 3 bit will identify the cache line. Okay. So, therefore, this A00 should be placed in the block 0 and rest will be the tag. So, therefore, here, so let us say here before that what you have to do, j equal to 0, then j equal to 0 in the jth block it should be A00, right, it should be brought to the memory. Next j is incremented by 1 and then you have to bring 0 1. Where is 0 1? 0 1 is here. If you carefully see 0 1 is here, that should be brought to the. So, 0 1 where it is stored, 0 1 is storing is 0 1 0 0, that means it is in the fourth position, right, fourth block. So, 0 1 0 0, because this 3 bit we need to see for the direct mapping. So, it is the fourth block. So, now in the fourth block here, so you have to write A01 because row wise we are computing. Next, what next? You again you have to do A01, A02. Then A02 where it will store? A02 will store again fourth byte, fourth word later. So, next will be what? Next will be A11, next will be 21, next will be 31. So, this was 100, this will be 101, this will be 110, again this will be 111 and next will be, say this will be A00, 01, this will be 02, this will be again block number will be, sorry, memory address will be 1000. So, now if you divide it here, so this will be in the block 0, but block 0 is already you have the some item here. So, therefore, you have to replace this one, because here we cannot use any replacement policy, because mapping scheme is only will be placed in the same location. So, therefore, this is after the first pass J0 and J1, when J will be 2, then this will be replaced with A0, this will be replaced with A20, okay, and this will remain same. Now, if J is incremented by 1, then this will go away, again it is by 4. So, you keep on data only this 0 block and the 4th block. Okay. So, in 3, so then you will have A 0 3. So, this is 0 0, this is 0 1, this is 0 2, so 0 2, this is 0 3. So, one row completed, and in this case there is miss, this is also miss because page is not there, and then you are replacing. So, therefore, if you increase this one, so j equal to 5, again you will replace here, you will replace here, and so on. So, at the last stage of the first loop, what is that? Here j value will be 9. Okay. So, what was the last 3? It will be what? 0 0. So, it is 10, right. So, it will be A 0 9. So, either in the first block or last block. So, then it will be in the 0 9. So, this side if j equal to let us say 9, because it will reach up to 9. If j equal to 9, then what do you see here? You have j 0 9 and here you will have a 0 8. Now, loop will be completed, right. So, here loop will be completed and compute the sum. Next, you have to divide. So, again you need 0 9, 0 9 is already in the memory. So, then there will be cache hit, 0 8 is also there. So, then there will not be any cache miss here. So, 0 9 is there, 0 8 is there. So, I value will remain same. So, I value starting from 9 and 8. So, if I equal to 8, this will be the content again. Okay. So, now if I is it is decrementing. So, it is 8. So, I equal to 7. So, then you have to identify the whether it is 0th block or the 4th block needs to be replaced. Okay. So, if you see I equal to 7, why 7? So, it was starting from 9, 8, yeah, then it will be 7 and then it will be 6. So, maybe after 6 what we will see. So, this will be a 0 6 and this will be a 0 7. So, odd bit odd index will be in the 4th and the even index will be in the 0, because that is 4 4 4 difference. So, that way if you continue at the end you will get I equal to 0 and that time you will have the content a 0 1 and then you will have the content a 0 0. So, in the next class we will continue with the same example, but different mapping scheme like associative mapping and set associative mapping. With this note I complete today's class.